Hi, I'm David Miguel from the French Atomic Energy Institute in Grenoble, France. So what I am doing is time result diffusion optical tomography. As we know, here in this field we can use different data types. So I'm trying to do theoretical numerical analysis. In the future I will do experimental analysis also. So in time result diffusion optical tomography, what we want to do is a three-dimensional mapping of absorption properties in the domain. And then we want to map them into oxy and deoxyhemoglobin. One of the problems is that we have to solve a time-dependent partial differential equation, and it takes a lot of time because we have to discretize the time in really small intervals. So for that reason, some researchers have proposed to use several data types, for example, like the temporal windows. In order to compute them fast, we have to use this kind of temporal windows where we have exponential and power functions. So what I am going to propose in this work is to compute efficiently different type of windows with unrestraining to this function. So how we do it? A temporal window is just this part of the expression. It's just an interval where we have the signal that we measure in the detector, and we have our window. So using the transfer theorem, we can pass it to the frequency domain, where we have the Fourier transform of both functions and also the conjugate of the window. So here we have temporal signals, and when we use the Fourier transform, we will have the spectral of each of the functions. So we can try to numerically integrate this part of the expression in order to get our data type. So one of the problems is, for example, windows, when we do the Fourier transform, how it affects the dispersion of the window. I mean, if here we have a really good time sensitivity, then if we do the Fourier transform, the window is going to be wider or narrower. For that, we can, for example, express the dispersion using this function. And we have, from the frequency theory or Fourier theory, we have this inequality that maybe it reminds you to the Heisenberg uncertainty principle for quantum physics. Here we have the dispersion in the time domain and also dispersion in the frequency domain. So we know that this has to be at least equal or bigger than this value. So what this expression is saying is that if we have here a really good time sensitivity, if the window is really narrow, in the frequency domain it's going to be wider. So we have to control that if we want to do easily the numerical integration. One of the windows that we can use is Gaussian window that we couldn't use before. The good point of this window is that in this inequality it's going to be equal. So this is a perfect window. As you can see, if in time result the window is wider, then in the frequency domain it's going to be narrower. And if it is very narrow here, it's going to be really wide. We can also use, for example, the key windows. These kind of rectangle windows, but we have a parameter, so we can adjust this parameter to make it go to a rectangle or more like a smoother function. And you can see that as the window is more rectangle, you will have also a lot of oscillations here, so you have to take care of it in the frequency domain. So why we are using these new different windows? I mean, why not use this expression? The problem is that here we have a lot of correlation. As you can see, as the windows go to the later times, they get more correlated. So here I have the correlation matrix. As you can see, for orders, as the order increases, it gets really correlated. And we don't really have good information. The noise gets really correlated. So if we use Gaussian or Tukey windows, you can see that the correlation matrix is almost diagonal. So I try to see if there is an improvement in the reconstruction. So now I am doing numerical experiments. So we have an inclusion with 3 times the absorption of the background, and here we are going deeper. The inclusion is going deeper into the domain. The sources and detectors are in the top. So you can see that in Laplace, after 2.5 centimeters, we cannot really locate well the inclusion. But if you use, for example, the Gaussian window, we can still see it and locate it well. It's true that it goes a bit wider, but we can locate it well. And another thing we can think about is maybe in the frequency domain, what we are just doing is fitting the frequencies, so why not use just the Fourier transform? And we can see that the results are quite similar to the Gaussian expression. So one of the questions that we can have from this experiment is that many Laplace and this kind of windows have a lot of correlations, so as we go deeper we have worse results. And is it useful to use these temporal windows, or we can just do frequency fitting and just forget about temporal windows? This is the question that I'm trying to answer in the future. So yes, a quick conclusion is that I am proposing a novel way to calculate a larger set of temporal windows. We can see that as we go deeper into the domain, we have better reconstructions, and in the future I will try to do numerical experiments in intralabit. And last but not least, I would like to give thanks to European Commission and Bitcoin Network for supporting and funding this project.